Okay. All right, so our objective today, we're going to be integrating vector-valued functions. And the integration, the indefinite integral, is fairly straightforward. If we have a vector or parametric equations, we'll just go ahead and take the integral of both the x-coordinate and the y-coordinate, as we see there. Just the big thing to remember is that both of these are going to have their own c value that we have to add for each part. So the y-coordinate and the x-coordinate have their own c value. So we just need to remember that as we are doing that integral. So that's our indefinite integral. We also have our definite integral, which is, again, very similar to what we know. We're just, as Spunden said, we have like two integration problems happen at the same time. And so we are going to be taking the integral, the definite integral of the x component, the definite integral of the y component, and so we see all that together. Again, we could separate that into two, we could separate that into two vectors if you really wanted to, but I think writing it like this kind of helps us just see we have those two separate vector or integral problems happening at the same time. Just noticed a typo in mine over here. Should be, what's my typo? B minus A, yeah, so that should be G of A. And then that will run into Spunden's two vectors down there too. So. Okay, so let's go ahead and just jump into a problem. I think you guys should be able to try that one on your own. We have our vector v, defined as t squared comma 1 over t. Go ahead and find the integral of v of t dt. Let's go ahead and try that one. Shouldn't take you that long. All right, so let's go ahead and do this one. We are doing the integral of vector v of t dt. So let's go ahead and do that. So that would be the integral of our x component, t squared dt, and the integral of our y component. All right, so what is the antiderivative for the x component? Someone's doing the derivative instead of the integral, right? And what do I need to add? Oh, I'm making a slight mistake there. There we go, that looks better. And we do need to make sure that we have the subscript on these because we do have two separate constants since we have two separate integral problems. So we do need to distinguish that. And then what would be the integral or antiderivative of our y component? Of t and then plus c2. And that should be good. What was that? So this would be giving us our position vector, right? If we counted this as velocity, then this would be our position vector. So yeah, the where we are physically at and where the particle is physically at. Yeah. Any other questions? Okay. So go ahead and try this one. We're doing a definite integral this time. We have our vector v of t. And we want to take the integral from 0 to 1. So we are taking our definite integral from 0 to 1 of our vector v of t. And so we just take the definite integral of each part individually. So let's go ahead and look at our antiderivatives here. I'll go ahead and write this on the next line down. Let's see, Camilla, what would be the antiderivative of the x component? Yes. Good. And then what would be the antiderivative for the y component, Thomas? Okay, so looking at here, we have 1 over t plus 3, so it would be the antiderivative. ln t plus 3. Good. Now, I was going around and I saw most of you, just write the bounds here, and that is definitely fine. I just wanted to mention you could, if you wanted to, you could also put it out here. That would be grammatically correct as well. Okay. I'm just going to go ahead and leave it in here because that's what we're a little bit more familiar with, and it makes sense on what we're doing. So we would do plugging in 1. What would we get?
We actually have to do it.
We're evaluating, so we're plugging in the bounds.
Then once it's plugged in, do we actually have to simplify?
Well, this one is actually very easy to simplify. We'll see, but if it was a free response, no, you could just plug it in and leave it as it is, right? Like normal. Negative second power, yep. Minus, so minus negative 1 to the e to the 0, right? Which would be plus 1/2, like you said, yes. That would be 1 plus 3 minus ln of 0 plus 3. So you have 4 minus ln of 4 minus ln of 3. So this one is pretty simple to simplify. We would just be left with negative 1/2 e to the negative 2 plus 1/2 and then ln. And we don't need the absolute values anymore because these are positive, so we can just write it as, that should be 4.
4 over 3.
You could write it as 4 over 3 as well. Yes, you could definitely do that. So that'd be another way of simplifying it even further. It's negative 1/2 e to the negative 2 plus 1/2. And that'd be ln of 4/3. There we go. Yeah. Again, you could always leave it up here at this step, but this one is fairly simple to simplify. Any questions on that one? It's fairly straightforward, right? We're just taking the integral, definite integral of each of the components here. All right, let's go ahead and try this one. So this one, you are given an initial condition. Notice how they're writing the vector again using those unit vector form, I and j. They might throw it at us that way, they might not, but we need to be familiar with that form. It's just another vector. So we have our vector RT is defined by the integral there. And find RT if R of 0 is equal to 1/2 I plus 1j. Let's go ahead and try that one out. So the notation. So just as a reminder of what we saw last week, that if I have a vector like 2, 3, it can be written as 2i plus 3j. The I and the j are unit vectors, and we can write, this is just another way of writing our vectors. So if you don't like the i's and j's, you can always rewrite it as a vector. It would just be sine of 2t, comma, this part there, and then over here it would just be 1/2, comma, 1. And so if you wanted to write it as the vector and the vector component notation, you could definitely do that. And Spunden's showing that how the unit vectors kind of get formed there graphically. But yeah, so that's just what the I and j is, just our unit vectors. If you wanted to write it back over in component form over here, you definitely could. And just work it that way. That makes sense. And as far as I understand, on like FRQs and stuff, it doesn't really matter which way you use, or whether you use the component form or the unit vector form. They will take either way. It doesn't really matter. As long as you are using vectors when they're asking you to use vectors, it doesn't really matter which form you write it in. So again, if it helps you, go ahead and rewrite it in component form like I did there. And then all we need to do is just take the integral, right? We have our two problems here. What is the integration or the antiderivative of sine 2t when I take the integral of that? So we have a little bit of opposite of chain rule, so U substitution happening in there. in the background. We could do that if we really wanted to, but we should be familiar. Negative 1/2 cosine of 2t plus c sub 1. And then what is the antiderivative of 1 over t squared plus 1? That is our arctangent or tan inverse. So arctan of 1 of just t, right? Arctan t plus c sub 2. Okay, so that is our, and that is what our vector rt is in our general form. Now we want a particular solution. So we're going to go ahead and use this initial condition that we have up here. So I'll go ahead and write that in component form as well. So that's 1/2 comma 1. All right, and really you're finding the, you're kind of have two problems. And if you want to split it into two problems and put it together back as a vector, you definitely could. What I'm meaning is that our initial condition is that we have x of 0 equals 1/2. And y of 0 is equal to 1. And we can go ahead and say, well, then our x of t that we found was the negative 1/2 cosine of 2t plus c sub 1. And then over here, our y of t is our arctan. You can do everything within the component form, but if separating it out and doing things separately helps you, definitely do that. It helps you kind of see where everything's going. And so we just go ahead and plug in our values, right? So that'd be 1/2 equals negative 1/2 cosine of 0 plus c sub 1. What is cosine of 0? It is 1, right? So then that would just be 1/2 equals negative 1/2 plus c sub 1. So what's c sub 1? 1. All right, and then over here we do the same thing. So 1 equals arctan of 0. What is arctangent at 0? It's 0. Remember, tangent is sine over cosine, so sine at 0 is 0, cosine at 0 is 1. 0 over 1, so we have 0. So then c sub 2 is just 1. And then we go back up and we're able to say what our particular solution now is. So our vector r of t for that initial condition is going to be negative 1/2 cosine of 2t plus 1, comma, arctan of t plus 1. They happen to come out to be both the same thing. Obviously, it won't always happen, but in this case it did. All right, so I have one more problem for you guys to try. We have our second derivative of our vector r given here. We have an initial condition for the first derivative, an initial condition for the original r of t. So go ahead and find r of t knowing those two conditions. All right. So one thing I just want to point out, I know you're still working through it, with the two initial conditions, remember if it says 3j, that's the same as 0i plus 3j, so we just need to recognize that our the I value there, the x component, is 0. And then similarly in the other one, 2i would be 2i plus 0j. And that's equivalent in that form. So we would have 0, 3 for the first derivative initial condition, and then 2, 0 for the original vector r initial condition. Okay? Just wanted to point that out as you're working through there. All right, so this is my velocity function. Are we good with that? I haven't done the other part yet. But are we good with the velocity function? I got negative 4 sine of t, comma negative 6t plus 3. Good with that? All right. I'll go ahead and do the other one. You can check your work with that. I'm forgetting my little vector arrows. Can't forget those. All right, so this is what I got for my final answer. How does it compare to your guys's? Good here? So I went ahead, I don't know if it's absolutely necessary, but since we have technically 4 different constants here, I went ahead and continued my subscript with C sub 3 and C sub 4 over here, just to distinguish that those are different than the constants that were over there. And then we got -2 for my C sub 3 and 0 for my C sub 4. All right. Any questions then with any of this? Pretty straightforward, right? All right. So you have about, 7 minutes or so. You can go ahead and start looking at the homework.